All right, in this video I'll be working through the second experiment from paper 3, the lab practical for ACE Physics. This was the one that was administered in 2019, May, June. And it reads, and it always says you may not need all of the materials provided. Okay, you may not need to use all of the materials provided. You can kind of see here all of the different materials that I've been provided with. Okay, so we've got a bowl of water, a 30 centimeter rule, 2 lids, 100 gram mass, some coins in a petri dish, and some paper towels. Paper towels. Okay, so those are the materials that are provided. I may not need to use all of them. The question paper reads, in this experiment, you'll investigate the upthrust on lids placed in water. You have been provided with 2 lids and some coins. Take the larger of the 2 lids. The diameter of the lid is D. The height of the lid is T, as shown in figure 2.1. Okay? Measure and record D and T. So you don't know how much pasta I had to eat this year, you guys, to procure these lab supplies, okay, to get the baby food too. So this is the larger of the 2 lids, and I will use my 30 centimeter rule here. And I want to be as accurate as the instrumentation allows me to be, and so I kind of want to round that to 6.5, but if I look very carefully, I would say 6.6 or 6.7. Okay, so, and that just kind of shows you the uncertainty is about 1 millimeter, right? That's the smallest division in the scale here. 6.6 centimeters. Note that I'm not restricted to any certain units. If you like to always have everything in meters, because that's the SI base unit, then you could just convert that to meters, so 6.6 centimeters. As I'm working through the lab, remember I'm mindful of all of the difficulties, the sources of uncertainty. And it's like the fact that the edge is rounded makes it a little bit difficult to sort of judge exactly. Should I measure to like the edge here, is like the very edge on this side? Look at the figure and it's kind of like, doesn't have that same kind of rounded property. So you might say it was difficult to, judge where the edge of the lid is, for this measurement. The thickness here, so T for thickness, right? And again, if I hold my rule up, remember, every time I make a judgment, I'm introducing uncertainty. So not only am I making a judgment about where does this line correspond to the edge of the lid, I'm also making a judgment about does this line sort of perfectly match up with 0. So uncertainty on both sides of that. And this looks to be about 1 centimeter. And it is. I would say it's exactly 1 centimeter. Okay, based on my judgment. So remember, you want to avoid rounding it just to like, oh, the closest half a centimeter, a meter, or whatever. But if it is exact, it's exact. Okay, so 1.0 centimeters is the thickness there. My next task is to estimate the percentage uncertainty in the value of D. Okay, so remember, how do we determine percentage uncertainty? It is the absolute uncertainty over the measured value times 100%. And the absolute uncertainty, I have to use the method where I'm using the smallest division in the scale, not half the range of values, because it's just a length where I shouldn't have a range of values. Like this did not change in length from the time I measured it a moment ago to if I were to measure it now, so I wouldn't have any range of values. I would just get the same sort of value again and again. And so I have to use the smallest division in the scale. So the smallest division in the scale for this is 1 millimeter, right? So each of these is a centimeter, but they're further broken down into 10 equal sections, right? Like a meter ruler usually is, or a 30 centimeter ruler. And so I would say that there's 1 millimeter of uncertainty on this side of it. There's 1 millimeter of uncertainty on this side of it. And again, because it's rounded, I kind of want to add in another millimeter of uncertainty because of that, you know. So in my judgment, I really think that there's about 3 millimeters of uncertainty there. If you look at how big that is, that's like, you know, this much, okay? So I'm going to say the absolute uncertainty is, we'll turn 3 millimeters into, so to turn everything into meters, or, you know, put it in centimeters so it agrees with this, I'm just going to use meters. So it's 0.003 meters of absolute uncertainty, right, 3 millimeters, divided by 0.066 meters, that's the measured value for D, right, 6.6 centimeters. So the units, as long as they're consistent, are going to cancel out anyway, right? It's a percentage. So the calculation becomes 0.003 divided by 0.066. It's about 4.5% uncertainty in D. Note that, you know, a mark for that and a mark for that. So 2 marks in the volume of the air space within the lid is V. Calculate V where the volume is pi d squared T over 4. So I'm going to use meters, so 0.066 meters squared times the thickness was 1 centimeter, so 0.01 meters over 4. And so this is just, you know, it's only worth a mark because you're just sort of plugging in the values that you've already measured into this equation for volume. Volume should be in cubic units, right? So cubic meters for this one. So I've got pi times 0.066 squared times 0.01 divided by 4 to give me a volume of 3.4 by 10 to the negative 5. Now, the amount of significance, so we can, in fact, is the next question, justify the number of significant figures you have given for your value of V. So we should do something to link the significant digits that went into the calculation, okay, to the significance here, all right? So you can see that I've got my thickness to, you know, 2 significant digits, I could say is 0.010, okay, or 0.066, 2 significant digits, all right, which is why I report my answer 3.4, right, 2 significant digits. The volume is reported to the same significance as the values D and T, okay? And if you would always choose the one with the least amount of significant digits, here they both have 2, you're not going to just use the one with the least sort of amount. Place the lid on the surface of the water so that it floats with its open face upwards. Add coins to the inside of the lid. After you've added n coins, the lid will sink. Report N. One, 2, 3, 4, 5, 6, 7, 8, 9, Now, it's 2 marks for this one. And anytime you're sort of measuring something, you should think about, do I trust that? What could I do to sort of, verify it, to further prove that, that's the right value here? I've got to repeat that trial. And because I'm working with, coins submerged in water, you think, why did they give me paper towels as some of my, sort of lab equipment here? This is where you have to kind of realize that in order to earn sort of the marks here, you really would need to repeat your readings on this. Let me show you what the mark scheme actually looks like here up to this point. The values of the raw distance and the raw thickness to the nearest millimeter with the units. And we did that. The percentage of uncertainty in D is based on the absolute uncertainty in the range 2 to 5 millimeters. So we chose 3 millimeters, right, of uncertainty there. Note that if you chose 1, that would be too low. If repeated readings have been taken, then the uncertainty can be half the range, but not 0. I don't know why they would ever allow that for a linear dimension, so don't get in the habit of doing that. If the working is clearly shown, correct method of calculation to obtain it. Correct calculation of D, justification of D linked to significant figures in D and T. It's exactly what we did, right? So far, so good. Now, value of N, we've got that. And if that's all you've got, you get a mark. But look, evidence of repeated N. So there is a mark right there for evidence of repeated N. So here, those coins, I'm not going to, so I want to reuse the same coins because these coins, were minted in 1992, and other ones in 1976, and they've had more wear and tear, a chance to gain more mass over, time, people touching them. So maybe that has something to do with it. Those are the sources of uncertainty that you're mindful of, to sort of report at the end of this. And so now we're just going to basically replicate that part of the experiment again. So I got my lid floating in water. Also, I think that the way that you distribute the coins inside of it makes a difference, right? So if I pile up all the coins on one side of it, then there's going to be sort of a moment of force about that, like a pivot, and it's going to start to tip, and as the water enters it, then it's just going to sort of, sink, when maybe I could have, if I would have spread them out more evenly, I could have fit more coins on there. And so I was somewhat mindful of that during the first trial there, to just kind of like put that one in the center, and maybe we just stack them up in the center. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 this time. So over here, I'm just drying those coins up, drying the lid off. Evidence of repeated readings. I always like a rule of 3. You're reading, I would do it 3 times. Doing timing oscillations, whatever it may be. Dropping coins and floating away. Note that I'm not leaving the coins wet, right? I'm actually drying them off in between trials. That could be a source of uncertainty, that the coins are wet, we use them after repeated trials, and therefore a little bit more massive. Those would be the sources of uncertainty that you could sort of point out at the end. All right, trial number 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So for the 3, so evidence of repeated readings, right? This is all the evidence they need to see, like you've done it, you know. And if you wanted to, you can make it very clear and say like trial 1, trial 2, trial 3, you know, n equals these values. So what value do I report here, you know, on this line? Anybody have an idea?
Half the range.
Well, remember, half the range is the way to get the uncertainty, but I actually just want the value of n, right, not its uncertainty. But you're right, you can anticipate sort of where we're going with this, right? There's some uncertainty in this, obviously, because there is a range of values. But to get like, well, how many coins did it really take? It didn't take 9, 12, or 13. It took 13 plus 12 plus 9 divided by 3. It took 11.3 points on average to sync that. So what happens, you know, are we allowed to do that? Sure. Okay. So on average, it takes 11.3. Even though I never put a third of a coin in the lid, that is the average of these values, and so that's what you would report as the measured value. And note the 2 marks, you earn 1 mark if you just left it at 9. Okay, you follow the procedure, you got it right. They don't tell you, hey, it's good scientific practice to repeat your readings for things like this. They're not friendly enough to sort of remind you of that. You say, you know what, I should check that again. So you don't know what it's going to be, but there's probably going to be something in the experiment where it's like, I need to repeat the trials here. And now it says take the smaller lid and repeat A1, B1, and C. And if we remind ourselves what that is, A1 were these measurements, okay? We don't have to estimate the uncertainties there. B1 was calculating the volume, okay? And then C was, you know, we just did those 3 trials. So we need to do all that with a smaller lid now. All right. So this. And so again, you can kind of see like there's the lip of the lid is sort of like flanged out a bit, and so it's not, you know, do I measure to like that edge or this edge? I'm just going to sort of be consistent, okay, with and try to measure it the same way I measured the first one, but list that as a source of uncertainty on that last page, where I can say, you know, it's difficult to judge where the edge of the lid is. You know, choose a lid that has a flat or a non sort of, you know, flanged edge or whatever, however you word that. All right, the diameter here, it's also maybe difficult to judge where the exact center is, right? Like, what if I'm measuring, like, you know, not the exact through the center of the circle? So that's another thing you could say. It's difficult to sort of judge that. So 5.0 centimeters. Now we want it to the nearest millimeter, okay? So if it's 5.0, right, 1/10 of a centimeter is a millimeter. So that's the level of significance we need to sort of report it to. If I just left it at 5, that would lose the mark, okay? Because that's not to the nearest millimeter. So 5.0 centimeters. The thickness now. .0 centimeters. You may recall that the volume was pi d squared t over 4, I think. Yep. And so now we can just calculate it as pi times, let's put it back into meters here. So we'll say that 5 centimeters is 0.05 meters squared times 0.01 meter over 4. Pi times 0.05 quantity squared times 0.01 divided by 4. So now I'm calculating the volume as 1. So it's 1.96. Okay, I'm going to say, well, I want to round that to 2 significant digits, so it doesn't round down to 1.9, it rounds up, right, to 2.0 by 10 to the negative 5 meters cubed. Note how I just was mindful of putting the units of my volume in there, and I thought, did I do that when I first did this? And note that I did not, and so I haven't submitted this paper yet for grading. And so I can find my mistake and correct it before I do it, right? Like there should be units with that volume. I plugged in meters, even though I measured these in centimeters initially, you know, I'm recording my volume in cubic meters. If you ever, you feel like, you know what, I need more paper towels for this lab. I was given 3 paper towels, but I feel like to get better results, I need more. Then you can request that of the supervisor, the lab supervisor. You can say, can I have additional, you know, so certain labs, there's additional supplies that the supervisor will have. It really depends on the lab. So like we'll see another experiment next week where we're sort of oscillating a magnet, okay, over a piece of metal. And the metal has like pieces of paper strips on it, so you can kind of make marks on it. If you needed like extra pieces of paper, you know, the strips of paper, because it's convenient, you know, there's some things you can request. You want to avoid asking the lab supervisor for help unless you're really stuck, okay? Like it's better to say, like the circuit, I can't set it up, you know, I don't know how to get this circuit set up. It could be that you have a malfunctioning apparatus, you know, like, oh, your multimeter is dead, you know, I'll give you a new one. That won't cost you any marks. In fact, you'll just be given extra time to complete it because we can't hold that time against you. But if it's something where it's like you didn't know the physics and now the supervisor has to like help you set it up, they'll make a note of that in their report and some marks will be deducted. But it's better to have like a mark or two deducted for major or minor help from the supervisor than to just sit there going, I don't know, you know, and you just like the whole lab period goes by and you haven't done anything. So it's like, you know, if you really are stuck, you know, you can ask the supervisor for some assistance. They'll make a note of it in their report and the correct number of marks will be deducted. And depending on whether it's minor help or major help, it could cost you like a mark or two. And it's usually for the data collection, like when we get to the data collection part of like experiment 1, not so much for this one. But you can always ask the supervisor for help. And they may or may not say like, that's not something I can assist you with, or it's like, okay, let me give you a hand. All right, so now we're counting these. 1.
Should you switch the camera?
Sorry, everybody, I was missing out on all the action over here. So now I've got 1 coin inside of my smaller lid. I got 2 coins, 3. I'm trying to like balance it out. 4, 5, and so that idea of like if you pile them up on one side, it's going to dip and then it will sink right away. I would definitely list that as a source of uncertainty because nowhere in the procedure does it say take care to evenly distribute the, you know, coins or something. So you'll sort of notice a very obvious kind of like, hey, there's a problem with this lab, you know, and again they want you to sort of find those sources of uncertainty and suggest things for improvement. Like how could we improve that? You know, you have to kind of brainstorm. So far I've got 5, I got 6, 7. And just like I did for the first one, I'm going to try to go through 3 quick trials of this. Tell the supervisor and the additional paper towel resources. Remember, we're investigating upthrust, and so it's like this thing doesn't sink because of the force of all the water molecules sort of crashing into it from underneath, but as the weight of this object sort of overwhelms that force of upthrust, that's sort of why it sinks. So things float because the upthrust force is stronger than the weight force. The ups are stronger than the down. 3, 4, 5, 6. Maybe say not using the same coins every time, you know, that's a source of uncertainty, that the coins might have slightly different masses and therefore weights, right? So just kind of keep an ongoing list of things, because you need 4 of them, right? By the end of the slide, we need 4 sources of uncertainty and 4 suggestions for improvement. You always got 1 in the bank, right? 2 readings are not enough. Take more readings and plot a graph. 4, 5, 6, 7, 7. So on average, you take that list, 7 plus 7 plus 6 divided by 3, 23rds, or 6.7 points, and there's the number of points in order for it to. Now they're probably going to tell us there's a suggested relationship between n and the volume or something. Why do we calculate that volume? Sure enough, there it is. It is suggested that the relationship between the number of coins that it took to sink the thing and the volume of air inside of that lid is this. They're directly proportional. Like you could fit more coins in before it sinks, directly related to the volume, and there's this K constant of proportionality. K is a constant. Let's calculate the K values, right? Because what did we want to do here? We wanted to test the relationship with K values. So the whole goal going into this. So I've got N1 equals K1, B1. N2 equals K2, B2. I kind of like to set it up like this, right? I'll remind myself of my original values here. So I have N1 equal to 11.3, and I'm going to divide each side by V1, right? Solve for K1. And so the volume that I calculated for that one was 3.4 by 10 to the negative 5. And the units here for N are just nothing, it's just a number of coins, but this is in cubic meters. And 2, I calculated it to be 6.7, and that's equal to K2 once I divide each side by volume 2, and this one was 2 by 10 to the negative 5 meters cubed. All right, so these are my sort of calculations. Note that my units of K are in reciprocal cubic meters, right? Like meters cubed in the denominator. So I've got 11.3 divided by 3.4 by 10 to the negative 5. They give me a K value of 332,352.9. And then you think about, like, should I just round up to 330,000? Should I have left this in cubic centimeters so I didn't get such a big number, right? It really shouldn't matter. Now we'll go over here. 6.7 divided by, in parentheses, 2 by 10 to the negative 5. And I get a K value of 335,000 even. And so now I want, let's report the answers. First value K, 332,352, 353, 335,000. This would be in reciprocal cubic meters. So meters to the negative 3, right? Plug the units for this. Explain whether your results support the suggested relationship. So here's where we need to say, if the percent difference in these K values is less than the percent uncertainty in the measured values of N or V, then the readings do support the suggested relationship. If we think about the percent uncertainty in sort of like this measurement, there's the range is 1, so half the range would be 0.5 over the measured value 6.7. So here's how you can calculate the percent uncertainty in this value of N. Half the range, so 0.5 divided by the measured value, 6.7. And so that gives me 7.5% uncertainty in that value of N. I did a similar thing here. I had a bigger range, right? So from 13 to 9 is 4. Half of that is 2. So 2 over 11.3. 2 divided by 11.3. gives 17.7% uncertainty in that value. You always want to kind of use the highest one. Like I'm not too certain about that, right? Like it took 9 once, 12, 13, maybe I should have discarded that 9 and said that was a fluke, I piled them up on one side. Let me do a third trial and see if they're closer to this, and I discard that as an outlier. If you're really doing this experiment as like a scientist, and you're like, I don't trust that measurement. For the purposes of this, it's like, we'll just, crunch it. Also in the interest of time. The percent uncertainty in V here, okay, we could calculate based on the percent uncertainties that sort of went into it. So remember, the percentage uncertainty in V, we calculated as 4.5%. But we're squaring, right? So remember the rule here. So it's actually 9% plus the percent uncertainty in this value of the thickness, which was the same 0.003 divided by 1. Because that was the measured value, so 0.003 meters divided by 0.01 meters. That's 30% uncertainty. There's 30% uncertainty in this value of t. So it's like we have 4.5 and 4.5 is 9 plus 30, like 39% uncertainty in this volume. It's a huge uncertainty, 39%. So the biggest uncertainty we had in N was 17.7%. The biggest uncertainty we had in V was 39%. Okay, so there's a huge uncertainty there. The difference in K is going to be 332,353 minus 335, right? Take the difference over the original value, 332,353. So you're good. So they're actually very close. They're only percent difference in K equals 0.79%, less than 1% difference. Those are almost identical. Okay, 332, 335, okay. Close enough that they're less than the percent uncertainty in the measured values, which suggests that the readings do support the suggested relationship. Percent difference in K equals this. And because this is less than percent uncertainty in V, which was 39%, right? You always just use the biggest one. Okay, like, it has to be less than the thing you were most uncertain about. Okay, it's less than the percent uncertainty in V. The readings are consistent, or the results are consistent with the suggested relationship. All right, to finish this paper out, it says theory suggests that K is equal to rho over M, where the density of water is given and M is the mass of the point. Use your second value of K to calculate the mass of the point, and then we give an appropriate unit. So the second value of K was 335,000, and that's equal to, now this is in per cubic meters, but look at the density of water that they give you in cubic centimeters per cubic centimeters, and so we do have to make a conversion there. I'd rather just convert 1 gram per centimeter cube, and so there's 100 centimeters per meter, but we got to do that 3 times. Okay, so in other words, we got to convert all of these cubic centimeters into meters, and so we multiply this by 100 cube. We have 1 times 100 times 100 times 100. So the density of water in cubic is 1,000,000. grams per meter cubed. Remember, this was in per meter cubed, so those will cancel out with grams. Solve it, multiply both sides by n, divide both sides by k. We got 1,000,000 divided by 335,000, and that yields 2.99, or about 3 grams as the mass of a penny that we calculated there. Second value then has to be less than the first. Valid comment, correct unit between 1 and 10 grams. They gave us the range. We saw there was 3. Okay. Here are the suggestions for improvement and the problems that they found with the lab. I'll leave it to you to kind of read through that. This is then a work example, paper 3 with Dr. Schleifer. See you next time.